Hello everyone, my name is Haofan. I'm a PhD student from UC Santa Cruz, advised by Owen Arden. Today I will be presenting our work, Secure Distributed Applications the Decent Way. Before jumping into the core content, I would like to ask a few questions. Let's say we have an order and billing service that we want to deploy to the cloud to process the order from the customer and bill to the customer. How do we ensure that the code execution will not deviate from the code we have deployed? A malicious host may tamper with the code execution so that customer's order may get altered, or the payment info may be leaked. In this case, the only solution is to trust the cloud who will obey the contract with us. But let's consider a different situation. The cloud service provides clients with access to digital contents, so it needs to deploy a program to the client to enforce the digital right management or DRM. How can the service provider ensure that the client will not tamper with the program to bypass the DRM? With enclaves, both of these problems can be addressed. The enclave is a cryptographically protected memory region that contains both code and data, so it provides integrity and confidentiality to data and code execution, and is isolated from all other software layers, so even some privileged layers like operating system can tamper with the code execution or access the data. Meanwhile, enclave can generate an unforgeable remote attestation report. The software vendor will record the hash of the enclave that is being deployed, and during runtime, the software vendor or user can compare the hash stated in the report to a known value. This ensures that the remote code execution will not deviate from their normal behavior, and the confidentiality of the data is guaranteed throughout the computation. This shifts the trust from the host to the enclave platform and the code itself. Now, let's say our business is growing fast. We hire a lot of employees and want to scale out the application into an order processing service and a billing service, so it can handle more requests and easier to maintain. Without relying on an external source, how do these two components verify each other? We may first think that they can embed each other's hash and then compare them during remote attestation. But will that work? Let's have a try. We first build the order processing code into the enclave binary, and then we embed the hash of the order processing enclave into the billing code, and produce the billing enclave. Now, if we embed the hash of the billing enclave into the order processing code, the binary of the order processing enclave will be updated, so do the hash. And then the billing enclave can no longer verify the order processing enclave. Thus, we realize there's a circular dependency. A strawman solution could be embedding the hash of the billing service into the order processing service, and that the billing service load the other hash afterwards. But the question will be, who gives this hash so we can trust its authenticity? Or we could have a single trusted entity to distribute the hash during runtime. But now, we not only trust the code, but we also have to trust this entity who could be a single point of failure. One working solution that we have found so far is to build all components into one binary and having a switch to activate different parts of the code. Since every node is going to have the same code, their enclave hash will be the same as well, so they don't need to know other hashes. Instead, they just need to make sure the peer has the same hash as themselves. But what if we scale out the application even more? This is a microservice architecture of Uber. There are a large number of components, where each one of them is responsible for a different job, so they can be maintained separately. If we use the aforementioned technique, we will be having a gigantic binary for each node. Meanwhile, if we update any single one component, we have to compile everything together and replace all the nodes with the latest binary. Therefore, building everything into one binary may work, but it isn't the real solution to the problem, since it's not scalable and will not work with the modern distributed applications. Even if we solve the mutual attestation issue, there's another issue. To further increase the scalability and availability of the application, we will need to have a large number of replications for each component. Instances of each component are created or destroyed dynamically based on the processing needs of the system. Therefore, each session tends to have fewer number of requests, and the lifetime of each instance is relatively short. That means we are going to have more sessions and therefore more remote attestations. However, remote attestation isn't just one message between two components. For example, in Intel SGX EPID remote attestation protocol, there are at least 5 messages sent back and forth between two components, and at least 2 messages between the verifier and the IS. So as we further scale out, the application will be overwhelmed by these expensive and repeated remote attestation messages. After we solve those two problems, are we done? No, because in the real world, all of these components will be updated during their life cycle. So there's another problem we want to address: how to let everyone knows the hash of the new component and revoke the old one. To sum up, in this work, we are going to build an enclave application framework that can support mutual attestation, provide low overhead for each session, and enable dynamic authorization of new components. So now, please let me introduce to you the Decent framework. In introduction, we mentioned that the circular dependency issue makes mutual attestation difficult. We also showed that loading the hash on one side raises the question of who should give this hash. So now let's see what could go wrong in such a situation. The client knows the hash of the order processing enclave, so it verifies the enclave and sends the order. Ideally, the order processing enclave loads the hash of the building enclave, so it can authenticate the building enclave before sending the data. However, the order processing enclave receives a malicious hash from the host. As a result, users' secrets such as payment info is sent to the malicious building enclave. To address the issue, a low-time auth list is required. The auth list is a map from the enclave hash to the name of the service. The service name is hard-coded at the build time, and the corresponding hash is loaded after the build time. And everyone in the system should agree on the same auth list. The load time is the earliest time we can configure the hash of the enclave. Once it has been loaded, the enclave will never modify the list. A malicious building X service will pretend to be a building service that has the same auth list, but itself is not on the list, so it's impossible to establish a connection to an honest enclave. The next issue we want to address is remote attestation's overhead. In the standard remote attestation protocol, components need to go through all of this process at the beginning of each session to authenticate the peer. Even though the enclave components may reside on the same platform, the similar remote attestation report is generated over and over again. So can we make remote attestation report reusable and verifiable by third parties? The answer is self-attestation. During program's initialization phase, the Decent server will generate a unique key pair and perform a remote attestation to itself in order to bind the unique key to the report. Thus, attackers won't be able to use that report to pretend to be the enclave, since they don't have the private key. And then the report and the public key are packed into a self-attestation certificate, which can be used to authenticate the Decent server by any third party during TLS handshake. Next, The decent component will also generate a unique key pair during load time, and it performs a local attestation to the local decent server, who will issue a certificate to the component. This forms a self-attestation certificate chain, where the decent server's certificate is verifiable by its remote attestation report, and the decent component's certificate shows it resides on the same platform as the decent server. The advantage of separating the functionality of decent server from the decent component is that each host only needs one decent server to perform remote attestation, and different components reside on the same platform can share the same remote attestation report. Meanwhile, since decent server and components are isolated enclaves, a malicious component won't compromise the server. Now let's have a look at how self-attestation and auth-list work together. The decent server first performs a remote attestation with the IAS to generate their self-attestation certificate. Next, decent components such as order processing service and building service are launched with their auth list loaded from the host. After that, they can perform local attestation to their local decent server to obtain the self-attestation certificate chain. Now they are ready for processing requests from the client. But before sending the data to the order processing service, clients need to ensure that the auth list held by the order processing enclave is the same auth list that they have. If so, the connection is established and data is sent. Same for the order processing enclave and the building enclave. They also need to ensure that they are having the same auth list before exchanging any data. Still, malicious hosts may provide an auth list that contains malicious building service component. But at this time, attacker will get nothing from such an attack, because the client will detect the unmatched auth list and refuse the connection. The previous solution only solved authentication and static authorization problem, but it's still hard to update enclaves and introduce new components, since auth list is configured at load time. So anytime when the auth list needs to be changed, we have to restart the entire system with the new auth list. To dynamically authorize new components, we use verifier, which are designated entries on auth list. For example, we can have a building service verifier that's designated to verify building service component. In general, the verifier has two tasks: verifying and authorizing new components. In verify step, verifier needs to ensure the new component is trusted to be added to the system and remember its hash. The verification scheme used by the verifier is application dependent. For that reason, we provide API to applications to accommodate their verification needs. For instance, verifier can collect votes from stakeholders to get consensus of the new version. Or even better, they can automatically verify the code inside the enclave using ideas similar to Ironclad from MSR. And then the verifier will authorize previously verified components by issuing certificates to them. Therefore, to join the system, the existing components will check that the new component has the certificate signed by the verifier, and the verifier is listed on the auth list. After adding new components into the system, we will also need to remove old or vulnerable components dynamically. There are two situations we need to consider when revoking the components. If the enclave platform is revoked, the decent server will fail to generate fresh remote attestation report. So components hosted on the same node will not be able to obtain a valid certificate from the server. If the vulnerability resides in the enclave code, we will need to revoke the specific decent component. which requires a mechanism similar to verifiers. Like verifiers, revokers are also enclaves. They are defined by the auth list. To determine the hash of the component that should be added to the component revocation list, we also provide API to accommodate application needs. For instance, they can collect votes from stakeholders to add a component to the revocation list. Or they can collect verifiable evidence, such as leaked keys or conflicting messages. To distribute the component revocation list, the Decent component periodically query for the latest list, so that attacker will get no benefit from suppressing the network message, because if there's no response from the revoker, the enclave will shut down to prevent further damage. The evaluation of Decent framework consists of 3 parts: correctness, expressiveness, and performance. To ensure the correctness of Decent protocol, we formally verified our protocol with ProVerif, which is an automatic verification tool for cryptographic protocols. An active attacker in ProVerif may read and manipulate any data on channels, and query messages derived from any obtained materials. And there are 2 security properties they will want to test with. The first is secrecy. Attackers should not be able to obtain the secret message that's being sent from one component to the other. The second is authenticity. Attackers should not be able to alter the message that is being sent from one component to the other. We ran the test for authorized app, which are apps listed on the auth list, and verified app, which are verified by the verifier who is listed on the auth list. The verification for secrecy and authenticity of authorized app is straightforward and fast, while the verification for secrecy of verified app took relatively long time to run. But the verification for authenticity of verified app is even more complicated, so we had to decompose the problem into 3 smaller parts and obtain the proof within a reasonable amount of time. To evaluate the expressiveness, we implemented a simple ride-sharing application based on the microservice architecture from Uber. The successful communication among 6 different Decent components shows that the Decent framework can support complex, decentralized application with multiple components. To evaluate the performance of Decent protocols, we implemented the DecentHT, which is a decentralized encrypted key value store based on core. We then set up the YCSB benchmark over DecentHT. To test the performance with different session lengths, we assign different number of requests to each session, and one mutual attestation will be performed at the beginning of each session. We compare the performance of DecentRide to 3 different groups. The SGXI groups use only the SGX remote attestation protocol, and 2 TLS groups use the same DecentRide protocol but running outside of the enclave. This graph shows the throughput of different groups in different session lengths, and we can conclude that the DecentRide provides significantly higher throughput in short sessions, while SGXI has to process more requests per session to compensate the cost of remote attestation. In this talk, we introduced Decent framework, which supports building complex decentralized applications with enclaves. Enclaves authenticate each other by using self-attestation certificates backed by remote attestation. The low-time auth list ensures that only authorized components can join the system. And verifier and revokers provide runtime modification to the set of authorized components. To ensure the correctness of Decent protocol, we successfully verified the data authenticity and secrecy of our protocol by using ProVerif. We also built 2 sample applications to evaluate our design. DecentRide shows the expressiveness of our framework, and the benchmark performed over DecentHT shows that DecentRide outperforms SGXRA in short sessions. Thank you for listening to our talk. We are happy to answer any questions you may have.